Alrighty, let's look at number 36. So we are supposed to either calculate the, so this is similar to our test now, isn't it? But we have to pick, either we take a divergence of this thing over the volume integral, or the surface integral of this thing going through that. And that surface integral looks very, very difficult now, doesn't it? Okay? So we'll go with the divergence and we'll think if we can pull this off. Okay? So derivative with respect to x first. So quotient rule. So denominator, you square this thing. So we have x squared plus y squared plus z squared cubed now. And then the numerator, we have to take a derivative of, which one should we do first? I think we should just suck it up and do it. You know what I'm saying? So let's do this first, x first. So we have 1 times this thingy, x squared plus y squared plus z squared, 3 over 2. So far so good. Minus, and then we have x times derivative of this thingy. Good. Okay, so times 3 over 2. Then we have x squared plus y squared plus z squared to the 1/2 power, and the chain rule, good, which is 2x. Okay, let me erase this thing and then say this is just the derivative, partial derivative with respect to x. Okay, so far so good. Now, how does this thing simplify? This thing simplifies to x squared plus y squared plus z squared. This is misleading, isn't it? Because if I say this, then that I vector, you know what I'm saying? How do I want to express this? Okay, I'm going to go back and we'll just do this divergence. So derivative with respect to x, this thing cancels, right? So do we get 3x squared? You guys all see that so far? So I'm going to get rid of this, and get rid of this. So what we end up having is 3x squared times this thingy. So far so good? That's just the x part. Now we take a partial derivative with respect to y. Okay? So plus here, same thingy, x squared plus y squared plus z squared cubed, and this will be the same, squared plus y squared plus z squared, 3 over 2. And then you will see this is very symmetrical. So you think we'll have 3y squared, x squared plus y squared plus z squared to the 1/2 power? You with me? And then you think z will look exactly the same except this thing is z squared? Say yes. So could we comment factor all that thing and then just combine it here and not have so much writing? This is what I meant. Okay, I'm going to come back here and move this thingy. Up like that. I'm going to move this thingy a little bit this way, and plus y squared plus z squared. This is what I meant. Do you see we are going to get exactly that and none of this? What the? Good. How do you like my lazy way of taking divergence? You with me? Okay. Now you can see we can potentially cancel some of this. right? But then let's simplify. I don't think we even have to cancel it. This is 3 over 2 power, isn't it? Oh, I forgot. I forgot little thingy. There's 3 missing here. Okay? Because when we do this with respect to x, I pick up one of this. Good? If I do it with respect to y, I pick up another one of this. And with respect to z, I pick up another one of this. So we should have 3 in here as well, right? That way, they exactly cancel. Good? Okay. Except there's one tiny mistake. So far, are you all with me why they cancel? Okay, what is a tiny little mistake? Tiny little mistake is, what about at the origin? Do we have 0 over 0? Yeah, we do. So we can't really do it. You know what I'm saying? This is what they call singularities. This vector field is very nice. So divergence is 0 everywhere outside, except at the origin there's a thing called singularity. So we can say this is true except at 0, 0, 0. Okay, so we have to worry about that, and we potentially have to calculate the divergence surface integral. Let's figure out what the strength of the vector field is at the origin, shall we? So now let's see. If the reason for this is because I want to compute this thing. Okay, how do I calculate the strength of this vector field? The denominator is already scalar, isn't it? So we can keep the denominator same. X squared plus y squared plus z squared to the 3 over 2 power. And the numerator, what's the magnitude of this vector? Is it square root of this square plus that square plus that square? Yeah, it is. So we take square root of x squared plus y squared plus z squared. So far so good? So this is a 1/2 power. This is 1/2, 3 over 2 power. So simplify, then we just said this. Now, what happens if we take a limit of this magnitude of vector as xyz approaches 0, 0, 0? Then do you see this thing becomes infinity? Good. What does it mean? This is exactly, you're not taking physics E&M, but if you have a point charge at the origin, all of the electric field is coming out from that little point charge, or from the nucleus of that thing, right? Because you can see the divergence is 0 everywhere else. So if there is any flux coming out, then it should be at the origin. The singularity is creating all of the charges everywhere. You know what I'm saying? So only field that is coming out, if any, there may be 0, right? But if this like looks like with a infinite amount of vector field, looks like everything is coming out through the origin. So far, so good. And this is the essence of Gauss's law in physics E&M, which you're not doing, but so let me draw a little picture for you. say this ellipsoid looks like this. Okay, now we have origin right here. Good. And then this is our surface. This is our S. We'll call it S2. Now, if I draw another surface around the origin, and I call that S1. If I take the flux integral of this thing over S2 of F dot dr ds, would that be same thing as flux integral over S1 of F dot ds? What do you say to that statement? Is it true? Yes, because everything that is coming out here, what color do I want to do this? Let's say blue. All of the charge that is penetrating one surface. Oh. Actually, that's how you draw a straight line, huh? That's amazing. All I have to do is put arrow, then it becomes this. I did not know that. This is convenient now. And then I have to end up drawing arrow twice. Well, how come that one didn't work? Let me try that one more time. Whoa! Didn't need to do that. Let me try this. That didn't work. Okay, fine, whatever. See, whatever is penetrating this S1 surface is also penetrating S2 surface because none of them are generating in the interior, it's only at the origin. Correct? So these two integrals are in fact exactly the same thing. So far, so good. So we will evaluate this integral instead. How's that? Good. Say yes. Okay, now we'll tweak it a little bit more. We'll go to other college notation. This thing is still same as 1, but we'll just say f dot n, normal unit vector, and yes, surface. Because that's what most books actually do. And you remember that MIT professor? This is kind of what they do in MIT, that NDS thing, right? With his French accent. Not that I don't have an accent, but he had a French accent. Okay, now we'll stare at this. Because why do I want this thing? Let's just look at this f dot n. N is a unit vector that is just sticking outside. Maybe I should throw it in. N is like this everywhere. You know what I'm saying? Because dot product is the magnitude of f times magnitude of n times cosine of theta now, isn't it? Say yes. Okay, how do I wanna say this then? Do I have to calculate what that n vector n is? I really don't want to do it. Okay. Oh, what happened? What did I do? I pressed something and that whole thing disappeared. Oh, we're in calculus. Okay, we're back. To use, I'm going to calculate that. I'm going to try to reason my way about pressing so many wrong buttons. Okay. let's just think about this thing. F dot n here. Okay. Let's push this thing downward a little bit. This thing does not want to move. It does. Do you see this has to be magnitude of f times magnitude of n times cosine theta? Do you see that? That's what that product is. Magnitude of f, we already have it up here, right? So we have 1 over x squared plus y squared plus z squared. So far, so good. What's magnitude of 1? And magnitude of n is 1, isn't it? So far with me? What is the angle that our field line makes with this normal vector? That's 0 degrees, isn't it? Because this normal vector is always perpendicular to this unit sphere, correct? So cosine theta is also 1. I'm going to actually write it. Cosine of 0. So what we end up getting is just this. Okay, on the Dropbox note, I actually computed the value of n. It's like, wow, when we get exactly the same thing, so should we, how many of you like to see what n looks like? And we can actually take a dot product if you want to. Virtual hand or real hand if you want to see what n looks like. Ne? Are we good? Okay, so we'll just trust this. Okay, then, now, yeah, so we'll go back up here. So this is, we can just convert this whole thing to this of S1 of 1 over, zoom in a little bit, x squared plus y squared plus z squared, and then ds. So far with me? So far with me? Okay. Now, on a unit circle, what is the value of this thing? Or should we go to spherical coordinate? Let's go to spherical coordinate then. So we'll have triple integral, double integral of, what is this thing? This is 1 over r squared, isn't it? So far with me? And we have, we'll just call it ds. But what is the radius of this thing? It's not just 1 over r squared. This is the unit sphere, isn't it? I call that radius 1. So r is equal to 1 over s1. So this thingy is really just this. You know what I'm saying? Are you all with me? Now, guess what that integral is? Yes.
Why is it r squared and not rho squared if it's spherical?
Rho, well, you have a point. Let's go back to rho squared. Yeah, it's technically rho. Where's my eraser? Why my eraser is not working? Rho squared, how's that? I probably should have put capital R squared. This is really, rho is not, I regret that. I just put capital R squared, how's that? Capital R meaning radius of the sphere that we are integrating over. So far, so good? Now, guess what that double integral gives us? We could evaluate it, but isn't that just the surface area of a sphere? Is it? And radius is 1, so this is 4 pi. How about that? So far, so good? So this entire flux integral becomes 4 pi. How about that? Are we good? Questions? Okay, then we'll move to problem 38. 38 looks like this. Ew, how did they come up with this kind of, right? Okay, we have to evaluate f dot dr. Good. And we really don't want to do such a thing because we don't even have an equation of this curve. So it looks like we are using Green's theorem or Stokes' theorem. Good. So it does look like we are supposed to calculate cross product curl of this field. Shall we do it? Okay, let's do it. Holy cow. That is awful. I, J, K out here, like that. So the x component is 2x cubed plus 2xy squared minus 2y. Not that. Hold on. Let's put that thing here, and this is partial with respect to x. And with respect to y, I'm gonna need a whole lot more space than these. So let's write that. That's the partial with respect to y. And then I have this thingy. So we have, over x squared plus y squared, of course. 2y cubed plus 2x squared y plus 2x over x squared plus y squared. And then, making a little more room. And then partial with respect to c, and this is 0. Good? Okay. Now this is equal to I vector. So this 0 and this is 0. There's no z. So 0 I vector plus y. That is 0 and there's no z. So 0 j vector. So only thing that survives this is this k thingy, right? So this minus this. So let's take a partial derivative with respect to x. Today is a quotient rule day now, isn't it? Okay, so we have x squared plus y squared, quantity squared, with respect to x. So this thing dies, so we have 4xy plus 2 times quotient rule, this thingy in the denominator, x squared plus y squared. Good so far? Minus, and that numerator, holy cow. So we have 2y cubed plus 2x squared y plus 2x. Looks like I'm not making this thing long enough. And then derivative of the denominator, right? Which is 2x. How about that? I did make this thing too long. You with me that much? And then minus, now I have to do this part, right? The derivative of that thing with respect to, oh boy, I'm gonna continue it downward. I'm gonna move the whole thing to the left. That's it. Hold on. Let's shove the whole thing to the left like that. Yeah. Okay, and denominator x squared plus y squared, quantity squared, And then we get to do this thing all over again. So derivative of the numerator this way with respect to y is 4xy minus 2. Good. Times x squared plus y squared minus, and that entire numerator, which is 2x cubed plus 2xy squared minus 2y times the derivative of a denominator, which is 2y. All of that thing with k vector. How's that? Very good? Okay. I really don't want to do it. Do you trust me that if this thing gives you 0 vector? It does, really, if you do it. It's like, once upon a time actually took a time to do it. Right? Once again, except at origin. You know what I'm saying? Okay, maybe I shouldn't write it like that. Except at 0, 0, 0. For the same reason. You know what I'm saying? Because denominator becomes 0. So we'll do exactly the same thing now. We'll draw the unit circle in the middle of this. Oh no, I pressed that button again. How come it goes back, but it never comes forward? That's a side button. There. Oh, yeah, we're back. See, this mouse that I'm using has a side button, and once I press it, it goes back to the previous page. With me? So why don't we draw that unit circle here? You know what I'm saying? Of radius 1. And then we orient this thingy that way, clockwise, so it's the same orientation. Okay, so here's my reasoning. Keeping that picture up here. See, originally we have the C, we'll call this thing C1 and that thing C2. So we have 5 minutes left. So over C1 of f dot dr is same as using the Green's theorem or Stokes theorem, whichever version you like to think of. And we call this entire thing D1. Good. Now, and then if we call that tiny area in here D1, because there's nothing, your curl is 0 everywhere except the origin. So only curl that occurs is at the origin now, isn't it? So this is same as D2. Oh, no, D2. D2 of curl of f dot dA. With me so far? As we compute it here, the curl is 0 everywhere except the origin. So only the swirling thing is happening right there. So yes. Now we use the Stokes theorem back to convert this back into f dot dr. So far with me? So far with me. Okay, now this is a unit vector. Okay, so we'll try to compute the length of this thing. Well, we have to compute this f dot dr, right? So we'll actually figure out the parametry. C2, this is C2 happens to be, let's say, R of T This is cosine t I vector plus sine t j vector, right? So the dr vector happens to be negative sine t I vector plus cosine t j vector, right? Yes. And then our f vector happens to be, now we have to substitute, where is my f? This thingy with the sine and cosine. That's a lot of work, isn't it? Yeah, let's do it. Suck it. How many minutes do I have left? Okay, we'll do it like this. Do you trust me if I say this f dot dr after substituting these two into our original thingy? That'll give us 2. You see? I mean, I have it in the Dropbox note. That whole thingy gives you 2. Okay? Now it's easy. Then this thingy is just from 0 to 2 pi of 2 to t, isn't it? And that gives you 4 pi. How about that?